Yeah. You can just speak.
Let me speak.
Will you introduce?
Yeah, but is it recording?
Yeah,
Oh,
it's recording.
okay. All right. Hayato is a postdoctoral fellow at Nagoya University and a GSPS research fellow. He received his master and PhD from the Graduate School of Mathematics, Nagoya University, under the supervision of Masahito Hayashi and Professor François Legal. His current research interests are in the foundation of quantum theory with information theory, general probabilistic theories, and the analysis of positive counts. Let us all welcome our speaker.
Yeah, thank you for the introduction. So today I'll talk about our recent work, derivation of standard quantum theory via state discrimination. This is a joint work with Masahito Hayashi. And so, do you want to know the detail about this work? Please see this archive paper. So firstly, I do myself introduction. So actually, very recently I moved to Riken from the Nagoya University. So another thing is just as a introduction from Leandro. So yes. Okay. Let's see. So today, I'll talk about my recent work on GPT. So this is related to my PhD thesis, but from now I'll work on more standard information theoretical topic like hypothesis testing or more mathematical topic about quantum information. So the foundation topic is not studied so much in your group, but this topic is well studied in your group. So I'm very happy to collaborate with you in the future. So anyway, yes. Firstly, so I believe I will give abstract of our recent work. So our recent work is addressed on the foundation of quantum information science or foundation of quantum theory. So our study aims to derive the model of quantum theory by using state discrimination in general probabilistic theories. And we give three results. So I'll explain the details in later. So anyway, this is a very simple abstract of our recent work. So and at the beginning, so I'll explain the outline of this talk. First, we give a brief introduction to general probabilistic theories. And in this introduction, we simply introduce some important pressing studies in GPTs. And then, so I'll explain the setting of our recent work about the title of this talk, and I'll give my main result of this work, and finally summary. And so in this talk, we do not give proofs of the result, but if we have enough time and you are interested in the proof, I'll give the proof finally. Okay, let's start with the introduction of the general probabilistic theories. So firstly, I'll give the motivation of the general probabilistic theories. So this is a foundational topic. So foundation of the model of quantum theory is still open. So even though the mathematical model of quantum theory success to describe our physics very successfully, very well. So For example, so Y, the mathematical model of quantum theory, is described as a Hilbert space or described as a positive symmetrical matrices. So such a problem is still open. So general probabilistic theory, okay, here after the GPT, is a modern approach to such aim to found or to characterize a model of quantum theory. And GPT mainly focus on the probability structure that is probability obtained by the state and measurement in a model. And GPT GPT impose only very natural and few postulates, mathematical structure on the model. So there are many available models in GPT except for quantum theory and classical theory. And many studies of GPT clarifies that classical theory can be easily characterized by many natural ways. On the other hand, it is quite difficult to single quantum theory out as a general models by using operational or physical, natural, or reasonable postulates. So this is the main aim of current studies of GPT, using the quantum theory. So, and there are many results for this aim, partial result, not partial, yes, so they are still open. And today we give brief introduction to GPT and such work of trial to single out quantum theory. Our work is also start with the same aim and same trial. But especially our recent work focus on the performance for information task as a postulate to drive quantum theory. So it is very important because such a performance can be regarded as an implicit limitation of physical experiments. And also this work, so derive quantum theory out of the restricted subclass of the model of GPT called quantum-like models. So we define we give the mathematical definition later. Okay, this is the motivation and somehow story of this field. And next we give the mathematical definition of the model of GPTs. So as a preliminary, we give the important mathematical object called positive cone. So before that, so we in the whole of talk, we assume that the H, we denote H is a Hilbert space with a finite dimension. And LH, H, and LH plus H denoted as a set of Hermitian matrices and set of positive symmetry matrices respectively. So then, so we define a positive cone. Positive cone is a subset of the finite dimensional real vector space with some inner product satisfying these three properties. So first, closed, convex, and has no empty interior. And second condition is closureness by the positive number multiplication. And second is some intersection condition. This simply this means that the positive cone is exactly not a vector subspace. This means that. So, but simply speaking, the positive cone is such a cone colored blue colored cone whose vertex is 0. And for a given cone C, we define dual cone as a set of all elements in the vector space satisfying the positive for any element in C. So like this figure. So in this case, a face of C and C dual is orthogonal. So here we remark that there are many ways to define the dual cone. So for example, so we can define the dual cone as an element in the dual of vector space, but such a definition is parallel, and for some later convenience, we define the dual cone in the original vector space. Anyway, so we give a typical example of the positive cone. So the typical example is a set of positive semi-infinite matrices. So in this case, the vector space is Hermitian, the set of Hermitian matrices LH. And also in this case, the dual is equivalent to LH plus itself. And here in after, so we consider only the case the vector space is Hermitian matrices and with the equivalence inner product given by trace. And then we define a model of quantums, model of GPTs. So in this talk, when we say that define a model, then we define three things: the state, what is the state, what is the measurement, and what is the probability obtained by state and measurement. And first, we start with a model of quantum theory for so easy understanding. So of course, this quantum theory is a model that state is given as a P of M, and the probability obtained by these two things is given by the trace. So, and the important thing about this definition is this requirement. So first, SLH plus means the state space, and MLH plus is measurement space here, and they are convex, and the probability is exactly positive, and the sum is equal to 1. This means that this value composes exactly probability vector, probability distribution. And in the whole of the definition of quantum theory, the set of positive symmetry matrices plays an important role. And roughly speaking, the model of quantum theory is determined by positive symmetry matrices. And the definition of the model of GPT is just a generalization from LH plus to a more general positive cone C. This is the definition. So the state is given as a normalized element in C, and the measurement is a family of the dual element, and satisfying the summation is equal to the identity matrix. And the probability is also trace, given by trace. And in this sense, a model of GPT is determined by the positive cone C. But also, this is the definition of the model of GPT. And we use the notation. Our state space is denoted as SC, and measurement space is denoted as MC. But here we remark that this is definition. This is a restricted definition of the restricted models of GPT. So in this talk, we call the restricted model is quantum-like model. So actually, so the model of GPT can be defined in more general vector space, abstract vector space, except for the Hermitian matrices. So, but today's talk we only consider these models about our recent work. So anyway, this is the definition. And in this definition, the state space can be illustrated very simply. So here is a positive cone C defining the model. And this condition, trace law is equal to 1, is can be written as a hyperplane in the vector whole vector space. And in this sense, the intersection is a state space. So this is very similar to the case of standard quantum theory. So, and why next, very roughly, I explain why do we consider such a restricted model instead by the general model of GPT. So as I mentioned before, a model of GPT can be defined in more general way, general object of vector space and in a product and positive cone. But our recent work need to compare the performance for state discrimination, as I mentioned later. So in order to this, so we need to deal with the trace storm. And then we need to consider LH, the set of Hampshire matrices instead of the general vector space. However, this restriction looks very strict, very strong. But actually, this is only the restriction about the dimension of the vector space. So we showed that. So if a model satisfies this condition, the model can be modified to quantum-like model, as I mentioned, as I defined before. Anyway, so we consider quantum-like model mainly. So okay, so we give some example of the quantum-like model, except for the standard quantum theory. So let us consider the case of the Hilbert space is the bipartite composite system, and its dimension, their dimension is equal to 2. And we consider, let us consider the case of the C is given as this set. So simply speaking, this is the set of unnormalized separable states. So next we consider what is a dual. The definition of dual is that in this case, and by Holtetsky PPT criterion, Peres-Holtetsky's PPT criterion, the dual can be written as follows by partial transposition map gamma. So this is just a result, the PPT criterion. And then the measurement is defined as the family of the dual element satisfying the sum is equal to identity. So we can consider such a non-positive measurement. So M0 is this one, and M1 and this one. So this one is not, so clearly this is not positive semi-definite, but this can be written as a transpose of positive semi-definite matrices. So we can, such a measurement is available in this model. This is the difference of the quantum theory between the quantum theory and quantum-like model. And by using such a measurement, so we can improve some information task sometimes. So here we give the result, give an example about perfectly discrimination, state discrimination. So this measurement can perfectly discriminate non-orthogonal separable states. This one and this one. So the perfect discrimination is means the same way as a standard quantum theory. In other words, this means that they satisfy this relation. So this is simply check this. And so as you know, in quantum theory, the perfect discrimination is equivalent to the orthogonality of the states, but clearly they are not orthogonal. So in this way, GPT, a model of GPT sometimes improve the performance for some information task, like such as state discrimination or something. And finally,
Sorry.
Yes. Yes. Sorry? Do you have any question? Please ask. There's no question? Randall, I cannot hear you. Randall, do you speak something now? I cannot hear you. But sorry, please wait.
Can you hear?
Yes, but very not clearly.
Yes, but not clearly.
Yeah, not clearly. So, but I can hear you.
Okay. So my question is, do you give the definition of capital gamma? It's a partial decomposition, but I didn't see the definition. Gamma.
Okay, definition of gamma. This is a partial transposition map. In this case, this map is such a partial transposition. So move to these 2 times 2 block matrices and transpose this matrix, these submatrices and this submatrices and these submatrices and these submatrices. This is the definition of the partial transposition.
Okay, I see. Okay, thank you.
Okay. Yes. So, and as a final topic about the introduction of GPTs in my talk, so we give some example, some study findings, present studies in GPT. So first, this is a very important finding. So in GPT, a model of composite system is not uniquely determined, even though the local models are fixed. So this means that a structure of entanglement so cannot be determined by simple postulate. So for example, non-signal principle and local tomograph postulate. So even though we impose this postulate and impose local structure is completely equal to standard quantum theory, but there are infinite many models, infinite many structures of the composite system. So, so this is but in the case of composite system of classical theory, this is very simple. In the case of classical theory, the composite system is uniquely determined as some independent product system. And moreover, this is the characterization. This can be regarded as a characterization of quantum theory. This means that so if a model has if a composite model has no entangled object, entangled state or entangled measurement, then such a model is only the case of classical. So this is very natural characterization of classical theory. And also, so classical theory can be characterized by broadcasting. So the possibility of broadcasting is very drastic difference between the quantum theory and classical theory. And in some sense of quantum information theory, the no broadcasting theorem or no cloning theorem is a special property of quantum theory. But this is not correct in the sense of GPT. In the sense of GPT, this is more correct. The possibility of broadcasting is special property of classical theory. So this is a very important finding of GPT. So simply speaking, so classical theory is very special case, but quantum theory is not special case in the model of GPT. And also for investigating the difference between the quantum theory and classical theory, it is important to consider the Bell inequality. But Bell inequality is not helpful for studying GPTs. For example, there exists a model called the PR box. This has a stronger correlated state than quantum theory. In other words, this model breaks the Trilson bound. And also, the entanglement structure whose local systems are standard quantum theory. So as I mentioned before there are infinite models of such model, but they have the same bound of Bell's inequality. In other words, they satisfy the Trilson bound. So in other words, Bell's inequality cannot detect the difference between these many entanglement structures in GPTs. This is also important finding of GPT. And finally, we give some, we mentioned that. So sorry, in this way, the many things considered were for distinguish the quantum theory and the other models of GPT, but such a condition is not successful to single out quantum theory, but so some mathematical property sometimes can drive quantum theory or very related to quantum theory. So for example, the strong symmetric condition derives algebraic structure like quantum theory. Yeah, so this is a very brief introduction of general probabilistic theory. And next we talk about our recent work. So first we give the explanation about setting of our recent work. Anyway, so our motivation is that so we define the quantum-like model in GPT. This is a restricted subclass of GPT, but our aim is that so we derive the quantum theory from these quantum-like models by using the performance for information task. Especially here, we consider the state discrimination. So I already briefly explained the definition of state discrimination. So in detail, I explained the detail, but this is the same thing as a standard quantum information theory. So we consider especially we consider the two-state discrimination. So the two-state discrimination is defined as information task. So given an unknown state rho and its candidate of two states, and we aim to identify the state rho by one-shot measurement with high probability. And in standard we determine rho is equal to rho I when I obtain the outcome I. And in this setting, there are two types of error probability, this one and this one. So this one means that so we determine rho equal rho 0, but actual state is given as rho 1. But this is so vice versa. So and we focus on the value of the sum of two types error, this one. So we denote it as this value as error rho 0, rho 1, m. So this value it can be regarded as a whole. This value is related to the error probability when the rho I is prepared with respect to with probability 1/2 with the same probability. And actually, so we can extend more general preparation probability P and 1 minus P. In the case, we need to consider P this one plus 1 minus p this one. So when we consider such a general case, the result is almost similar. So, but our current version of the archive paper, we did not deal with such a generalization, but we'll update the generalization soon. But anyway, so in this talk, we consider the simple case that rho I is given with probability 1/2, and we consider this error probability 1/2 error probability. So, and so in the case of the error probability is equal to in the case of this value is equal to 0, then the error probability is 0, and we call this case path discrimination. And as you know very well, so preceding study, there are many preceding study about state discrimination in quantum theory. So as I mentioned before, the path discrimination is possible if and only if they are orthogonal. The states are orthogonal, and also it is well known that this is bounded by the twice norm as this inequality. Today's talk, we call this inequality quantum bound. And also there are preceding studies. Actually, this is our preceding study. So in GPTs, in certain quantum-like models, both of the relation, this one and this one, can be compatible. In other words, there exist perfectly distinguishable non-orthogonal states. And this means the violation of the quantum bound, because if they are non-orthogonal, then this value is exactly strictly less than 2, and then this value is strictly larger than 0, but this is 0, and then this means that violate this inequality. And our question is that when such a violation emerges in general, can we give equivalent, for example, equivalent condition in general case? This is the start question of our work. So, okay, I'll give main result. So actually, so the answer is very simple. So for to mention to state the answer of this original question, so as a preliminary, we define the value range of the measurement. So for a given two outcome measurement, we define this value defined as the maximal eigenvalue and minimum eigenvalue, so as the difference between the maximal eigenvalue and minimum eigenvalue. So this definition looks somehow strange, but because this is not described as the index I, but so this is a measurement, and therefore the sum is equal to identity, and then the maximal eigenvalue can be maximal eigenvalue of M1 can be written by the minimum eigenvalue M0, vice versa, and then this value is independent with the choice of I. Then, so this is a well-defined thing. So anyway, so by applying this value range of the measurement, we obtain the lower bound of error probability in general quantum-like models. So this is the theorem one. This is our first result. So consider a quantum-like model defined by a positive constancy. Any pair of two states in the model in the state space of the model, and any measurement in the measurement space in the model satisfy this general bound with error probability. So this is very similar to the quantum bound. The difference is just the range And so in quantum theory, so the measurement is P of M, and the measurement matrix, candidate matrices is less than identity. Therefore, they have only the maximal eigenvalue is less than 1, and the minimal eigenvalue is larger than 0, and then the range is less than 1. And by applying this inequality, we obtain the quantum bound to this one. Very simple. So this is a also so this theorem states that if the range is strictly larger than 1, a model can violate the quantum bound. So in other words, this is necessary condition for the violation of quantum bound. And very simple, very surprisingly, this is also sufficient condition. So as a result, we obtain equivalent condition for violation of quantum bound as this theorem. So consider a quantum-like model defined by positive constancy. So and given a measurement in the model, the following two conditions are equivalent. First, there exist two states in the model satisfying this inequality. In other words, violate quantum bound by this measurement. And the second is range is strictly larger than 1. So here we explain the brief sketch. So the implication 1 to 2 is shown by theorem 1 already. Very trivially. So and the implication 2 to 1 is shown by the exact construction of the state satisfying this. So if I have enough time, we give the explanation, we get the proof to exactly construct the states satisfying this inequality. And this theorem mentions that if there exists a measurement satisfying this, then the model violates quantum bound. Very simply. So this is the answer of my first question, when the quantum bound is violated in general quantum-like models. So the answer is simply the range is strictly larger than 1. And by applying this theorem, so we can derive the quantum theory and additional condition. So consider a quantum-like model defined by positive constancy, and we impose additional condition, this inclusion relation. This means that the measurement space of the model is larger than the measurement space of the model of standard quantum theory. In other words, this condition is that the all P of A can be available in this model. So under this condition, the following two conditions are equivalent. First, the positive con is equal to the positive semi-finite matrices. In other words, the model, this model, is equivalent to quantum theory. And the second is that any two states in the model and any measurement in the model satisfy quantum bound. So in other words, under this condition, all P of M's are available measurement in the model. The quantum theory is worst model in terms of the probability of state discrimination. So if they satisfy quantum bound, sorry, there exists only model satisfying quantum bound. The model is just quantum theory. This is meaning of the theorem 3. And implication 1 to 2 is just a result of standard quantum information theory. And non-trivial thing is the implication 2 to 1. So in this case, we can construct a measurement satisfying this under this condition. This also this condition can be changed. This condition. So anyway, sometimes one can consider what is a non-trivial thing. So the non-trivial thing is that if we assume this, then it is not trivial. We can always take a measurement satisfying this because when we in the case of the model satisfying this inclusion relation, even in the case, so we only consider the measurements that are non-positive. But even if the measurement composed of non-positive matrices, the range of the measurement, range of the maximal eigenvalue and minimum eigenvalue is not always larger than 1. So for example, they only have very small positive eigenvalue and very small negative eigenvalue. In the case, the range is small, but this is not P of n. So this is a non-trivial point. So even though this inclusion relation satisfies, it is not clear. It is not trivially to take a measurement satisfying the range is strictly larger than 1. But mathematically, but as a result, it is possible. This is the theorem 3 and our main result of derivation of quantum theory under condition. And also, one can consider that this additional condition is very strong, but in some sense, this is very natural assumption as follows. So then let's consider a quantum-like model, and we consider that in the case we embed each state space of the quantum-like model into the state space of the quantum theory. So when we embedded this quantum-like model as such, sorry, when we embedded state space of the model into quantum theory, into the state space of the quantum theory, then this inclusion relation automatically holds. And in this case, the model completely similar in quantum theory. In other words, not only the state space, but also measurement space can completely contain quantum theory, that of quantum theory, if and only if it satisfies quantum bound. So in other words, so quantum similarity, the similarity of quantum theory can be completely characterized by quantum bound for state discrimination. This is very surprising result, I think. And when we consider such a similarity, so this condition automatically holds. This is the meaning of this theorem. Okay, I summarize this talk and we give some open problems finally. So in my introduction to GPTs, so there are many models in GPT except for quantum theory. And some property is drastically changed in the model of GPT. But so sometimes this is this situation, and due to this situation, we encounter the mathematical difficulty, but the sum of error can be well solved even in quantum-like model, and the result is very similar to quantum theory. So as a result, we obtain new general bound of error probability, and we obtain equivalent condition for the violation of the quantum bound of error probability. And by using this, quantum theory can be characterized by quantum bound and the condition about measurement. So in the midpoint. So quantum similarity can be completely characterized by quantum band of state discrimination. This is a new approach to derive through performance for information tasks. This is the main take-home message in our talk. And this is just the end of my talk without proofs. So firstly, anyway, thank you for your attention. Thank you for your listening. So at once I want to ask, so is there any question about this talk?
Hayato, can you hear me?
Yes, yes.
Okay, thank you for your presentation.
Yes.
I suspect that the audience has any questions.
Hi, Hayashi. Thank you for the talk.
Yes.
So you hear me?
Yes,
so,
but not clearly. Please speak more loudly as large voice.
Okay. Okay. I'll try to speak louder.
Ah, yes, nice, good.
Okay. So my question is, you basically use the stack discrimination to derive new quantum theory, and I'm wondering what's the is there any constraint or limitation of the size of the two, the row 1 and row 2, the dimension? Is there any influence for their dimension? Are they not?
Yes. So, yeah, exactly. So this is an important thing. So I forget to give up open problems. So this is related to the open problems of 3. So this is exactly true. So we assume the definition of the vector space as a square. So, and in this case, we can describe the state as by the Hermitian matrices. So we assume that states can be described as Hermitian matrices in mathematically. So is it answer your question?
Sorry, I didn't quite get the point. You mean can you say again? You mean the size must be equal to the dimension, or can you repeat? Sorry.
Okay. So I don't catch your question. I don't quote your question. I didn't catch your question. So first, I don't assume the additional condition of the dimension of Hilbert space in whole talk, but so our results are valid in the case we define today. We define this model, but actually this is not the general definition in GPT. So the difference is just a dimension. So we assume the dimension of the vector space as d square in some d. Then our result is valid. Our results are valid, but in general case it is open. This is one of the open problem of our talk related to this one. Can I answer your question?
Yeah, I think so. Thank you. So,
yeah, thanks so much.
Can the stack discrimination extend it to multiple states, more than 2 states?
Yeah. This is also important thing, and so this is related to our open problems we forget to explain. So this is important thing. So in our talk, we mainly based on the one-shot measurement. And of course, we can consider, for example, IID case or something more headshot asymptotically case. This is important of problem, or some extension to the more hypothesis testing scenario, like Stein's lemma. This is also important of problem. Maybe when we consider such a more general thing or more detailed difference about hypothesis testing or something, also we can derive quantum theory by another way, more detailed, I think, I hope. But this is very difficult thing for mathematical problem as a mathematical problem. But so this is very important.
I see. So can I ask, what's the general goal of this field, the quantum foundation field? Are you deriving more less constrained mathematical structure to describe the quantum system, or what's the general goal of this direction?
Sorry, what? So do you ask the definition in the case of general model of GPT?
Maybe
Okay, I cannot catch your question.
Like, is there any common goal for all those different GPT try to achieve? What's the goal of this new derivation of quantum theory from GPT? What's the goal of
Okay, I see. Yes. So to be honest, I don't know. But my hope is that by developing these studies, so we can give some take-home message about the foundation topics, like this one or this one. So, and in this sense, information. So, our performance for information task is very important, as I mentioned firstly. So for example, such a limitation of the performance, for example, for state discrimination, can be regarded as implicit limitation of physical experiments or something like that. So my hope is that by using such a findings or such a knowledge about foundational topics about this one, then we can give so it is possible to give some contribution to actual experimental physical things. For example, when the quantum theory reduces the classical theory or something like that. So our ultimate hope is such like so, and the ultimate goal about GPT is like such a thing, I think. But this is my opinion. This is my idea.
Yeah. Okay. Good. I think that's important. Yeah.
Mm-hmm.
But I'm wondering what's the difficulty for combining all these new idea like information into the quantum theory? Is the difficulty lying on the derivation of mathematical structure, or it's more like a consistent definition, the heart of the difficulty of consistency of definition? Usually, what's the obstacle?
Sorry, what? Finally, what do you say? I can hear your final sentence.
Can you hear me?
Yes.
Okay, I'm asking what's the difficulty here? I mean, is the definition like consistent definition to the current quantum theory, or is like a mathematical problem difficulty? What's the difficulty here?
Yes. Yeah, main difficulty is mathematical thing. So as you know, so quantum information theory is based on the positive semi-infinite matrix, and this case is very special case in mathematically, and this is very so there are very helpful property for the positive semi-infinite matrices. but so in the study of GPTs, we cannot use such a helpful structure, helpful property, or helpful theorems in the preceding work. So this is a difficulty, main difficulty of the study of GPT.
Okay, thank you. I think that they all answer my question. This foundation problem is really important, and thank you for your talk. Thank you.
Thank you so much. Thank you so much.
Okay. Do we have more questions? Let's wait for them to think a little bit.
And I forget to explain this open problem. So especially first thing. So this the relaxation of the additional assumption of theorem 3 is also open. This means that can we relax this additional condition? Actually, I don't have any counterexample for the relaxed version of the theorem 3 without this additional condition. This is also open problem. I just forget to say this.
Okay. Okay.
And this thing is already explained in the last questions.
Mm-hmm. You mentioned to Ming-Chen that your hope is that studying these things we can get better insights into quantum theory itself, right?
Yes. But that is I think very ambitious ambitiously goal, I think.
Okay. Yeah, certainly. I wonder, is there any setting that we know that we have this the sets of measurements and states that we could actually try to test those things? Because I'm not sure if this is more like a mathematical construction to try to and test the boundaries, or we can do anything on a lab as well, or it's like some sets of measurements that leave in some space.
Yeah. This is important problem. So there are some trials, and so this is not. So this is formally sequencing, but so actually I give a result like the simulation of such a general models. So please see the new footprint. Maybe I give it this year. So actually, your point is very important, and recently such a topic studied somehow.
I think we don't have any more questions.
Okay.
So let me thank you again for accepting coming here.
Thanks so much.
I'm going to stop the recording now.
Okay.